Hello everyone, welcome to Chemazon-Complete Chemistry. So in this video we are going to learn how to draw the molecular orbital diagrams that for polyenes, that is for ethene, for compound having two double bond, that is 1,3-butadiene and 1,3,5-hexatriene. Okay, that is for polyene system. We will see the frontier molecular orbital or FMO theory. Okay, this is very important to understand. It is important to understand this FMO theory first, and then we will see its application in how in electrocyclic reaction or cycloaddition reaction, how this theory can be applied. Okay, but before that we must know what exactly is this theory. Okay, so there are certain rules for drawing the molecular orbital diagrams. Now these are same for the molecular orbital diagram that we draw in organic chemistry for, let's say, diatomic molecules, homodiatomic and heterodiatomic molecules. Same applies here as well, because here also there will be combination of atomic orbitals. Atomic orbitals will be mixing and give rise to the molecular orbitals. Okay, but any atomic orbital can mix or combine to give molecular orbitals? The answer is no. There are certain rules. So the first one is, it is called as a linear combination of atomic orbital, that is LCAO. Okay, now what is the meaning of this? That atomic orbitals, okay, combine to form the molecular orbital. Okay, now any atomic orbital can combine to form molecular orbital? The answer is no. Okay, so which orbitals can combine? The molecular orbitals which have the similar energy. Okay, which have the similar energy and the appropriate symmetry. For example, an s orbital combining with s orbital, they both have similar energy. Let's say 1s and 1s combining, so they have same energy. Shape or symmetry is also similar, that is both are spherical in shape. For example, a p orbital combining with another p orbital, or p orbital combining with an s orbital. Okay, they have similar energy and the appropriate symmetry. And the last one is, how many molecular orbitals will be formed? It will be same as the number of atomic orbitals that are combining. Okay, let's say 2 atomic orbitals are combining, we will get 2 molecular orbitals. 4 atomic orbital combining, we will get 4 molecular orbitals. 6 atomic orbitals combining, we will get 6 different molecular orbitals. Okay, these are the 3 important rules that we have to remember. Okay, now this is a very basic example, that is a 1s orbital combining with a 1s orbital. Now when 2 atomic orbitals are combining, it gives rise to 1 and 2 molecular orbitals. Now there is one lower energy molecular orbital that is called as a bonding molecular orbital, that is more stable because it is lower in energy. And then there is a higher energy molecular orbital that is called as a anti-bonding. Now you have to remember that for lower energy we write sigma, and to indicate the higher energy orbital that is called as the anti-bonding molecular orbital, we indicate with a star, okay, or an asterisk like this. The star means it is anti-bonding. Okay, similarly pi is bonding, pi star will be anti-bonding. Let's say delta star, delta is bonding, delta star is anti-bonding. Okay, so now what gives rise to this bonding and anti-bonding molecular orbital is the phase of the orbital. Now s orbital can have one phase, that is plus, another possibility is minus. Now same phase, if they combine, plus and plus combine, it is same phase that will lead to bonding. Okay, that will give rise to bonding molecular orbital like this. Or let's say minus and minus combining, they will give rise to bonding. If opposite phase orbital combine, you will get something called as the anti-bonding molecular orbital, and then there is a region, okay, where the electron density is what? 0. That is called as the plane. If you draw plane across that is called as a nodal plane, and the dot is called as a node. Node is the region where electron density is 0. Okay, like this. So a region, a point where there is 0 electron density is called as a node, and the plane that you draw is called as a nodal plane. Okay, this was for the s orbital. Now what about the p orbital? That we are going to see now. That is the first molecule, that is ethylene. Okay, what is ethylene? CH2 double bond CH2. Okay, now here there is one pi bond. So how this pi bond might have been formed? By the overlap of two p orbitals. Okay, so by the overlap of two p orbitals. And there is another important point is, as the energy increases, the number of nodes will also increase. Okay, so how do you draw? First you draw the energy axis. Okay, and then two atomic orbitals are combining, right? One p orbital and another p orbital. Okay, so two atomic orbitals, that is two p orbitals are combining, so that will give rise to two molecular orbitals. Okay, one is the lower energy. Lower energy, we represent this as a psi. Okay, this is pronounced as psi. Okay, written as psi, pronounced as psi. Okay, and then there is a middle line like this. Okay, so the lower energy, they are what? They are bonding molecular orbital. And the higher energy molecular orbital, that is the anti-bonding. So there are two molecular orbitals that are formed, right? So the lower one, we write it as psi 1. Okay, psi 1, and the another one, higher energy orbital, is called as psi 2, and I told we represent it with a star or asterisk. Okay, and then there are how many pi electrons? 2 pi electrons. So how do you fill? You write 2 dash like this, that represent the energy level. So according to the Hund's rule, we always fill the according to the electron filling rule, lower energy orbital is filled first, and then this should be paired first. Okay, two electrons in the lower energy psi 1, that is a bonding molecular orbital, and only 2 electrons, so there will be no electron in the anti-bonding molecular orbital. Okay, psi 1, psi 2. Now what about the nodes? Here in psi 1 there will be 0 nodes. Okay, psi 2 there will be 1 node. And how do you draw the phases of this? 0 node means plus, minus. Okay, when the node is present, the phase will be opposite, but no node, so the phase will remain same. Okay, same phase orbitals are present. Okay, for the anti-bonding, this will be plus, minus, and then there will be one node. Okay, and we draw the nodal plane. Okay, node means the other orbital will have the opposite phase like this. Okay, plus and minus will overlap, that is opposite phase of lobes of the p orbital will overlap to give the anti-bonding molecular orbital. So how does it look? Like this. Okay, here they have shown in terms of shade. Okay, here you can see red and red, same shade orbital are overlapping, that means it is same phase. And in case of anti-bonding, red and white are combining, that is opposite phases. Okay, now let us see when there are two pi bond, that is 1,3-butadiene. This is 1,3-butadiene. 1,3-buta means 1, 2, 3, 4 carbon. At the first and third position there is a double bond. Now there are 2 pi bonds, so 4 p orbitals will be involved. Okay, so 4 atomic orbital are combining. So how many molecular orbitals will be formed? Again, first you draw the energy axis. From bottom to top, energy is increasing. Okay, there will be 2 bonding molecular orbital, and then there will be 2 anti-bonding molecular orbital. Now how do you fill the energy? Okay, electrons 1, 2, 3, 4 energy level. This one will be psi 1, psi 2, psi 3 and psi 4. Okay, before that, in the previous one we did not mention the HOMO and the LUMO. Okay, here there will be the lower energy. HOMO means filled molecular orbital, so this one is the HOMO, highest occupied molecular orbital, and psi 2 is what? The LUMO, lowest unoccupied molecular orbital. Okay, similarly here also we have to mark the HOMO and LUMO. That is why this theory is called as a frontier molecular orbital. Frontier molecular orbital means the combination of highest occupied and lowest unoccupied. Now 4 pi electrons. So 1, 2. Now psi 1 is filled. You fill the psi 2, 3 and 4. Okay. Then this will be psi 3 star and psi 3 4 star. These are what? Anti-bonding molecular orbital. Psi 1 and psi 2 are bonding molecular orbital. Okay. Now what we have to do? We have to fill the phases in this. Okay. So psi 1 there will be 0 nodes. Okay. Psi 2 there will be 1 node. Psi 3 there will be 2 nodes. Psi 4 there will be 3 nodes. Okay. Now how do you fill the phases? So if this is plus, this will be minus. Here there are 0 nodes, so all will be same phase. Minus, minus, minus. Okay. In the psi 2 there will be 1 node. Remember this number of this molecular orbital and the number of node. Number of node is 1 less. So suppose if there is psi 34, then there will be how many nodes? 33 nodes. Okay. For psi 3 there are 2 nodes. Psi 4 there are 3 nodes. So psi 34, let's say hypothetical molecular orbital, there will be 33 nodes. Okay. So this is lowest one. Now psi 1 there is 1 node. Now where you have to place the node? It should be symmetrical. So we will place the node at the center like this. Like this. Now you fill the sign plus, minus. Then there is node. No, there is no node, so phase will be same. Okay, then there is one node, so third one the phase will be opposite, minus, plus. Then is there any node here? No. So the fourth one the phase will be same like this. Now 2 nodes, where you will put the 2 nodes? One will be here and one will be here. Okay, so draw the nodal plane like this. Okay, so first one plus, minus, node. Then so the sign will be opposite, plus, minus. In front of minus there will be plus. Now is there any node? No. So third one will be same as the second one. Now fourth one, again there is a node, so the sign will change. Okay, plus will combine with minus. Okay, and the last one is very simple. There are only 3 possibility and 3 nodes are present. So you draw the nodal plane like this. So plus, minus, now all will be opposite sign. Again node is present, so minus, plus. Then again node is present, so opposite sign. Then node, so again opposite sign like this. So in this way you fill the phases of the molecular orbital. And how does it look? It looks like this. Okay. So in textbooks they directly draw like this, so it is very difficult to understand. Okay. So that is how I have shown you step by step how to draw. Okay, so psi 1 you can see there is 0 node and they have shown the bonding interaction. That means same phase overlap, there is 1, 2, 3 bonding interaction. In psi 2 there are 2 same phase overlap, that is why they have written 2 bonding interaction. Okay, and what about the HOMO and LUMO? So in bonding molecular orbital, HOMO, highest occupied molecular orbital. Occupied there are 2, psi 2 and psi 1, which is higher in energy, psi 2. So HOMO will be psi 2. And what will be LUMO? Lowest unoccupied molecular orbital. Now unoccupied is psi 3 and psi 4, which is lowest in energy, psi 3. Okay, so LUMO will be psi 3 star. Okay, that is what they have given in the next slide. HOMO is psi 2. Okay, and LUMO is what? Psi 3. So why we got these 4 molecular orbitals that they have given? If there is same phase overlap, there is 2 possibility. In opposite phase overlap also there is 2 possibility. So that is why we will get 2 bonding, 2 anti-bonding, a total of 4 molecular orbitals. Okay, then last one we are seeing 135 hexatriene, that means 6 atomic orbital are combining. So we will get 3 bonding molecular orbitals. Okay, these are the bonding molecular orbitals. Then separation, and then there are 3 anti-bonding molecular orbitals. Okay, so you draw the energy axis, you draw all these orbitals, and then now we have to label them. Okay, this is psi 1, psi2, psi3. Now anti-bonding. So star, psi4 star, psi5 star and psi6 star. Okay, now you label the nodes. 0 node, 1 node, 2 nodes, 3 nodes, 4 and 5 nodes. Okay, and how to fill the electrons now? 1, 2, 3, 4, 5 and 6. Okay, so 6 pi electrons, so 6 electrons, 1, 2, 3, 4, 5, 6. So this is the highest occupied. So here HOMO is what? HOMO is psi 3. And these are the unoccupied, which is lowest in energy, psi 4 star. That will be the LUMO. So in this way you identify the HOMO and LUMO. And why this is important, that we will see in the next video. Okay, now we have to fill the phases. Okay, phase of the okay, 0 node, it is simple, all will be same phase. Okay, plus, plus, minus, minus, plus, 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 minus, minus and minus. Okay, and then psi2 there will be one node, so we'll put the node here. So these three will be same. Okay, plus, minus, plus, like this, and then there is a node, so the other one will be opposite. This one will be minus, plus, so this one will also be minus, plus, minus and plus. Okay, one node. Now two nodes, where you will put two nodes, one will be here and one will be here, like this. Again you will fill the signs like this, plus, plus. Okay, then node is present, so opposite sign. Again node is present, change the sign, minus, so it will be plus, plus, minus, minus, like this. Now the last one, bonding molecular, anti-bonding molecular orbital. Now here there are three nodes, so where you will put the three node, 1, 2 and 3. Okay, so plus, minus, then node is present, so change the sign. Then no node, so minus, plus, then again node is present, change the sign. Again for the last one, node is present, so change the sign like this. Now the next one. Now 4 nodes, so 1, 2, 3 and 4, like this. How you fill the sign? Plus, minus, node is present, so change the sign, minus, plus, again node is present, change the sign, plus, minus, then no node, so it will be same, plus, minus, and for the fifth one, again node is present, so change the sign, and last one, again node is present, so change the sign, plus and minus. Now the last one. Okay, all 5 nodes are present, 1, 2, 3, 4 and 5. So the signs will be opposite, plus, minus, minus, plus, plus, minus, minus, plus, minus, minus and plus. So in this way you have to fill the phases of the atomic orbital. Okay, so here you can see. Okay, so the node was in the middle, then like this, then 3 node, 4 and the fifth one. Okay, so they have given the bonding orbital, HOMO and LUMO we have already marked. Okay, now there are two things, one, either there will be a thermal condition or there will be a photochemical condition. Okay, light. Thermal means heat, photochemical means light. Now in thermal, the HOMO LUMO is same as we saw just now. Okay, HOMO is psi 1, LUMO will be psi 2 star. Okay, the way we have seen just now. Okay, but the problem is when you have a light condition. So in light, what will happen? One of the electron from HOMO jumps to the LUMO. So HOMO will have like this, LUMO will be like this. So in light condition, HOMO and LUMO will change. So accordingly, the orbital overlap will also change, and the product that we will get, that will be different. Okay, so it's very important. Thermal and photochemical condition, we must know how to identify the HOMO and LUMO. In some net paper or previous year GATE question paper, they've directly asked what is HOMO and what is a LUMO. Okay, not asking the product of the reaction or something. Directly they have asked what is the which molecular orbital is HOMO and which is LUMO. So ethene, you can see one electron jumped from psi 1 to psi 2 star. So HOMO is psi 2 star, and there will be no LUMO because there is no unoccupied orbital. Okay, in butadiene, HOMO was psi 2, but here the HOMO is what? Psi 3, because the electron jumped from psi 2 to psi 3. So this is the higher energy filled orbital or occupied orbital, and there is only one unoccupied, that will be the LUMO. Similarly, here previously in Hexatriene, psi 3 was HOMO. One electron moved from psi 3 to psi 4. So psi 4 became HOMO, and previously psi 4 was LUMO. Now the psi 5 became the LUMO. So this difference we must know, it's very important. That's it for this video. I would end this video with this beautiful quote. Okay, be kind to others. Your act of kindness might become someone's memory of a lifetime. Okay, in the next video we will see exactly how this orbital overlap and how the stereochemistry is determined in case of electrocyclic reactions. Thank you. Okay, I hope you have understood all these molecular orbital diagram, how we draw it.